Greetings and welcome to your lesson 1 on algebraic expressions. Okay, so today we're just going to be looking at the number system. So as we know that about numbers. So if you don't know your numbers, you don't know math. Okay, now listen to me. Numbers, okay, are divided into two subsets when it comes to mathematics. No matter where you go, no matter where you are, numbers are just divided into two subsets. We've got real numbers and unreal numbers. All you have to know. So after now, we are therefore going to be looking at all the different types of real numbers and all the different types of unreal numbers. So what makes numbers real numbers, and then what makes numbers unreal numbers. So stay tuned. Okay, so when it comes to unreal numbers, okay, so these numbers are for me, I always call them the numbers whereby it's numbers that we have them theoretically, okay, but in actual fact those numbers don't exist, right? And then the best way to test the whether or not numbers don't exist, so one practical way is to test them in your calculator. So the first type of number that we regard as an unreal number is a square root of a negative number. Okay, so let me expand on this a little bit. Okay, so what is a square root? Okay, so I hope you recall, and then you also remember that in your earlier grades we said 1, 4, okay, 9, all right, 16, 25. Okay, we call these numbers perfect square. Okay, and then why do we call these numbers perfect square? Right, it's because when you say 1 times 1, you'll always get 1. When you say 2 times 2, you'll always get 4. When you say 3 times 3, you always get 9, 4 times 4, and so forth, right? Then what we also notice here is that even if you multiply negative numbers of these numbers, let's say for example you say negative 1 multiplied by negative 1, you'll always get a 1 still as well, the same one that we got there when we said a positive 1 times a positive 1. Seemingly, if you say negative 2 times a negative 2, you'll get a positive 4 still, because we said when you're multiplying, you always multiply your signs first and then you multiply your numbers. So negative times negative, whenever you're multiplying same signs, you'll always get a positive sign, and then 2 times 2 is 4. Okay, now you recall that we said if you're multiplying a number by itself, okay, you can always convert that expression, okay, in that number raised to a power of how many times that number is being multiplied by itself. For example, 1 times 1 is the same as 1 squared, okay, because when you say 1 times 1, it's two ones multiplying each other. Seemingly, 1 times 1 times 1 is the same as 1 cubed, we said, because it's 1 multiplied by itself, and then there's 3 ones in this instant. So I'm basically simplifying this and explaining this because I want to explain what a square root is. Okay, so if you ask yourself a square root, so what you're saying is, what is the number that I will multiply by itself, okay, in order to get a specific number? So for example, we call 1, 4, 9, 16, and 25, we call them perfect squares because there's a number that you can multiply by itself or square in order to get them. So hence we call them perfect squares. But however, 3 and 2 are not perfect squares. Okay, why? Because number one, they don't form this list, okay, which we call perfect squares. And then number two, there's no straight number or perfect natural number that you can multiply by itself in order to get them. So we call them numbers which are not perfect square. There is another specific name for them. It's just that I don't want to use it here so that I will not confuse you. Okay, now I hope you can see now that whenever you square any number, whether you're squaring a positive number, okay, whether you're squaring a positive number like here, okay, because you say 2 times 2 is the same as 2 squared, the answer is always a positive number. And whether or not you're squaring a negative number, because we said negative 2 times negative 2 is the same as negative 2 all squared. So even if you're squaring a negative number, your answer will always give you a positive number. So therefore, if you say a square root of a negative number, let's say maybe negative 9, okay? Now, if you punch this into your calculator will always give you an error, okay? Why? Because there's no number that you can multiply it by itself in order to get a negative number. Okay, so that's why a square root of a negative number will always give you an unreal number. That's the explanation behind. And then any number divided by 0, okay, will always give you again an unreal number. So you can try it now in your calculator. It'll always give you an error. So in other words, if you have, say maybe you're trying to say 5 divided by 0, okay, 5, okay, divided by 0, this will always give you an error, or what we call undefined. Okay, right. So any number divided by 0 again is an unreal number. So guys, don't forget, there's 2 types of numbers that we call unreal numbers. Number 1, a square root of a negative number, okay, and any number divided by 0. So remember guys, we said square root. So square root means here there is a 2. Okay, so this is important because a cube root, okay, of a negative number is not an unreal number. So for example, a cube root basically of, say maybe negative 27, okay, is actually existing, okay, and then it's basically your negative 3. Okay, so when it comes to cube root, this rule here does not apply. It's always a square root of a negative number, okay? But when it comes to cube roots, no, it actually does not apply, okay? So in fact, it's a root of an even number. So it's a root of, say, maybe 2, 4, 6, 8, and so forth. So all those numbers are even numbers. So any root of an even number will always give you an unreal number. Very important. Okay, so now let us move on to our next section, real numbers. Okay, right. So real numbers, they basically there's basically a variety of them. Okay, but to basically expand and explain real numbers in more detail, I just like us to basically look at some background knowledge that I feel as if we will need to understand before we understand what real numbers are. Okay, because I'm going to be using these terms quite a lot. So for me to basically use them nicely, you must be in a position to be understanding them. So what are natural numbers? Okay, so natural numbers are, I say, for most people, it's the numbers that we knew all the way from grade R or from grade 1. Okay, so it's your numbers starting from 1 and increasing all the way to, say, maybe whatever. It can be infinity. But then these numbers actually does not include fractions. Okay, so a symbol to represent your natural numbers, it's your capital letter N. Okay, and then these numbers, okay, we said are numbers that basically start from 1, okay, 2, 3, 4, and so forth, all the way up until infinity. Okay, I think the second type of numbers which we introduced to you are numbers that we call whole numbers. Okay, I think after you're introduced to your natural numbers, the next set of numbers is whole numbers. So what are whole numbers? Whole numbers are your natural numbers but starting from 0. So I think that was the second type of numbers which you were introduced into. So the symbol for your whole numbers is a capital letter N with the small O there in the bottom. So these are your whole numbers. So your whole numbers are your natural numbers but starting from 0. So 0, 1, 2, 3, 4, and so forth. Okay, very important. Now, what are integers? So I think integers again were the third type of number, okay, that you were introduced into. I think at some point you were told that numbers do not only exist only as positives, but we also have negative numbers as well. So hence we call those numbers integers. So it's the same numbers that will exist in something that we call a number line, which I believe you must be in a position of knowing it by now. But if not, you are going to be learning a lot on number lines, as you are going to be using them quite extensively in your 10th grade. So when it comes to your integers, the symbol used for your integers is your capital letter Z. Okay, then we said our integers are nothing more but your natural numbers, but also including your negative numbers as well. So think of it of like having your 0 here in the center, okay, and then moving to your right hand sides, basically towards your positive numbers. So let's say maybe you've got your 1 there, you've got your 2 there, you've got your 3 there, you've got your 4. Not only that, but also moving in the same way towards your left hand side, but moving in a negative direction. So -1, -2, -3, -4, and moving forward and moving forward. Okay, so I know this might be basic, but I'm going to say it anyhow, that as you move from 0 all the way up, your numbers are increasing, but as you move from 0 all the way down, your numbers are decreasing. So these are your integers. It's basically a set of number system that actually also include your negative numbers. Okay, so guys, this basically form the background of the type of numbers that you must know in order to understand your real number system. Okay, so when it comes to real numbers, okay, they are basically categorized, okay, or divided into basically two sets of numbers. Okay, so it's divided into your rational numbers as well as your irrational numbers. Okay, so basically when you basically explain what your real numbers are, so it's basically any number on your number line. Okay, so it's basically a combination of rational numbers and irrational numbers combined. Okay, now so when it comes to rational numbers, now I think it's important for us to explain what rational numbers are. Okay, so a rational number, okay, just for your ease of reference and easy clarity, okay, a rational number can be expressed in a form of A over B, okay, where A and B basically represent your unknowns, okay, or basically your variables. So what did you say a variable is? A variable is any letter, okay, that represents an unknown number. So in other words, if you've got a number as your numerator and then your number as a denominator, that basically represents what your rational numbers are. But there's an exception, okay? This B here can never be equals to 0. Okay, I hope you can remember why. Because we said any number divided by 0 is actually an unreal number. But remember, we are talking about real numbers here. So B can never be equals to 0. It cannot be equals to 0. Okay, right. Now, this is basically what your real numbers are. And then your A and B has to be integers. So in other words, your A and B has to be equals to integers. So therefore, this is what rational numbers are. Okay, so maybe just to quickly summarize, a rational number is a number that can be expressed in a form of A over B, where B is not equals to 0 and A and B are integers. Remember what we said integers are? Integers, all your numbers, okay, basically in the number line, but basically your whole numbers, as well as your your whole numbers, as well as your natural numbers, but then also looking them in the negative spectrum as well. So we said those are basically what integers are, okay? But remember, B can never be equals to 0, okay? B can never be equals to 0, but A can. That's very, very important for you to remember, okay? So rational numbers also include proper and improper fraction. It also include terminating and recurring decimals. So I'm going to be explaining what these are, okay, just in a minute. So in other words, whenever you see a whole number, so that whole number will always be classified as a rational number. Whenever you see an integer, that integer can always be categorized as a rational number, okay? Whenever you see a proper and an improper fraction, those can always be classified as a rational number. Again, whenever you say terminal and recurring decimal, they can always be classified as a rational number. Okay, now let me explain what proper and improper fractions are, because I think you guys know what whole numbers are. You also know what integers are. We did explain them earlier on. Okay, so a proper fraction, okay, is whereby your numerator is than your denominator. Okay, so for example, right, so for example, 1 over 2 is a proper fraction, okay? 3 over 2 is basically, this is not your proper fraction, okay? But okay, so this is not your proper fraction, all right? But 1 over 4 is your proper fraction. 2 over 5 is your proper fraction. Why? Because your numerator is bigger than your denominator, okay? And then improper fractions are incidences whereby your numerator is basically bigger in this case than your denominator. So for example, 5 over 3. Another example can be 4 over 1. Okay, another example can be 7 over 5. So all these are improper fractions, okay? So I hope you can remember in your earlier grades that we are able to basically change an improper fraction into a mixed number. So what is a mixed number? So you get your mixed numbers by changing improper fractions in this way, okay? So what we normally say is, we say, okay, my 5 over 3 is basically a mixed, is basically an improper fraction. It can be changed into a mixed number this way, by saying how many times does my denominator goes into my numerator. So how many times does my 3 go into 5? Then the answer is it goes once, okay? And then what's the remainder? Okay, then the remainder, okay, is going to be 2, because when you ask yourself how many times that does it goes once, and then there's only 2 left. So your remainder is 2 over your denominator of 3. Now this, guys, is called your mixed number, okay? So again, your mixed number fall under your rational numbers, okay? Now what is a terminating decimal? Okay, I hope you guys know that when it comes to fractions, you can always represent them as fractions. You can also represent them as ratios. You can also represent them as decimal fractions. Okay, now a decimal can be represented as, or can be called, or can be categorized as a terminating, non-terminating, a recurring, and a non-recurring, right? But when it comes to terminating and recurring decimals, they both fall under rational numbers. So whenever you see a terminating decimal and whenever you see a recurring decimal, you must know that that is a rational number. Now, what is a terminating decimal? Okay, so a terminating decimal, okay, is a decimal that has a finite digit or a last digit in it. Okay, so it does not extend or continue basically continually. Okay, I hope you get my point. So for example, if you look at 0.25, okay, we're now looking at terminating decimals. Okay, if you look at 0.125, okay, now we've got the last digit here, and then the last digit is 5 after the comma. Okay, now because there's a last digit after the comma, now we call this decimal a terminating decimal. So it terminates, it ends. Okay, so that's what is a terminating decimal. Okay, right. I hope you guys know, I hope you guys can remember how we basically used to change our decimals from our earlier grades, like simple decimals like this. You'd ask yourself that okay, if I've got 0 on my left hand side, a comma, and then a terminating terminating numbers after my comma, then I always write them as the numerator. So I'm going to make my numerator to be 125 all over. Okay, then as long as I've got a 0 there, I can always treat my comma there as a 1, and then ask myself how many numbers are found after the comma. So 1, 2, 3. Then I'm going to make a number of zeros after the comma, which is equal to the numbers which are after the comma. So what question to ask myself? It's okay, if I've got a decimal that is terminating and the 0 in the beginning. So what I do is I take the numbers which are after the comma, I make them to be the numerator, and then I say all over. I treat my comma as a 1. I write the 1 there, and then I ask myself how many numbers are after the comma, and then if there's 3, I write 3 zeros. If there's 4, there's 4 zeros, and so forth. So that's how you change your terminating decimal into a fraction, okay, which is always your proper fraction. Now this can be further simplified by asking yourself how many times does 125 goes into the numerator and the denominator, and then in this case 125 goes once into the numerator all over, and then 125 goes 8 times, okay, into the denominator. So therefore this is a terminating decimal, and then it can also be converted into a fraction. Remember what we said? We said our decimals can always be converted into fractions. Okay, right. And then when it comes to recurring decimals, so it's basically a decimal again. Okay, a decimal, a fraction represented involving a comma. It's a decimal that has number 1, it does not basically terminate, okay, and then number 2, it basically has a pattern after the comma. So for example, when we look at 0.3333, okay, which can also be written as 1 over 3. If you can punch this into your calculator, you'll notice that you're going to have 0.3333, and then this will never end. Okay, so you can always represent this by like 3 dots or so after your last 3. So by writing dots after your last 3, what you're trying to tell us is that this will always continue basically up until infinity. 3s or so are found after the comma. Okay, so it does not terminate, it does not end. But as much as it does not end, but then there's also a pattern of 3s after the comma. Okay, right. And then on the other side, or on the other hand, sometimes your recurring decimal that does not have to have like same numbers. So let's say maybe for example, you've got 0.1234, 1, 2, 3, 4, and then I put my numbers like that. So what we notice here is we've got a 0 and then comma. So as much as we don't have a same number after the comma, but then there's a pattern. We've got 1, 2, 3, 4, and then after 1, 2, 3, 4, another 1, 2, 3, 4 starts. Okay, now because there's patterns after the comma, this also falls under recurring decimals. It's non-terminating, but then it's recurring because there are patterns after the comma. Okay, right. So now we're going to be moving on to our irrational numbers. So what are our irrational numbers? Okay, or before we continue, okay, let me just also add this here as well, that when it comes to our rational numbers, okay, also square roots of perfect squares fall under rational numbers. So for example, square root of 9, okay, we know that this is equals to 3. So we know that 3 is also what? A whole number. And then a whole number is a rational number. So therefore, a square root of a perfect square automatically falls under rational numbers. Another example will be a cube root of a perfect cubed. So in other words, the cube root of 8, okay, is basically equals to 2. And then we know that our 2 is also an integer or a whole number. So therefore, we know that a whole number or integer falls under rational numbers. So therefore, square root, okay, of a perfect square will fall under your rational numbers, and then your cube root of your perfect cube again will fall under your rational number, because the answer that you get from there is an integer. You can also call it a whole number because this is an integer and it is still a whole number. Okay, right. I hope that was clear. I hope that was clear. Now let us move on to irrational numbers. Okay, now remember we said a terminating decimal is a decimal whereby we find a term that is the last term after the comma. Okay, now a non-terminating decimal, okay, is a decimal that basically does not terminate, but it has to be non-recurring for it to fall under our irrational numbers. Okay, then we said on top, a recurring decimal is a decimal that will always fall under your real number system. Okay, right. So for example, okay, so for example, we are going to be looking at some examples onto what form of a decimal actually constitutes non-terminal and non-recurring. Okay, now it's important for me to say at this stage that these decimals cannot be represented in a form of a ratio between integers. Okay, I'm going to explain what this actually means. Right. So, but these numbers, okay, are basically square roots of numbers that are not perfect square. So another easy way to actually look at this is to basically know what your rational numbers are, okay, and then anything that is not a rational number will automatically fall under irrational numbers, provided it is not an unreal number. Okay, so for example, okay, a square root of a number that is not a perfect square, so maybe a square root of 2. Now this number here, if you punch it in your calculator, okay, I'm just going to do it here because I've got my calculator next to me. Square root of 2, okay, is basically 1,414213 all the way across. It basically is basically a decimal that is actually non-recurring. So therefore, square root of 2, okay, is basically irrational because it's a non-recurring decimal. There's no pattern. There's no pattern after your comma. Okay, that's your first group of numbers that falls under irrational numbers. Okay, number 2, again, a cube root of a number that is not a perfect cube. So we remember that our cubes are basically 1, 8, okay, 27. So these numbers here, you've got to say, you've got to take a specific number and cube it in order to get them. So for example, if you say 1 cubed, it's the same as 1 times 1 times 1, which is the same as 1. If you say 2 cubed, you have to say 2 times 2 times 2, which is same as 8. And then if you say 3 cubed, okay, so you have to say 3 times 3 times 3, and then you will get 27. Now these numbers here, we call them perfect cubes because there's a number that you must take and then cube it in order to get them. But however, if you take any number that is not a perfect cube, that will always give you an irrational number. Remember we said a perfect cube will always give you a rational number, but however, a number that is not a perfect cube will always give you an irrational number. So for example, a cube root of say maybe 4, okay, because remember 4 is not a perfect cube, but it's a perfect square. So therefore this will give you an irrational number, okay, an irrational number. So other numbers, okay, that can actually fall under the category of your irrational numbers, okay, can actually include basically your pi, okay, your pi, okay, which is written with this symbol, I hope you know, which can be represented as 22/7, okay, but then again, this here does not fall under your rational numbers because you'll notice that it's a fraction that actually does not terminate, okay, but it also is non-recurring, and as there is no pattern at all after your comma, okay. So I hope guys, with this lesson here, you were able to grasp and understand what rational numbers are and then what irrational numbers are, okay. It's important for me again to say at this point that both rational numbers and irrational numbers are found on the number line, and then they all constitute real numbers, okay. So what real numbers are? Real numbers are a combination of rational numbers and irrational numbers. I hope you remember what we said unreal numbers are. And then under rational numbers, now you must know that rational numbers are made up of whole numbers, they're made up of integers, they're made up of proper and improper fractions, they're made up of terminating and recurring decimals, and so forth, okay. So guys, it's bringing me to the end of this lesson, okay. Other than this, I've got a homework after this, okay, or a task for you to do. So I urge you to please try and do it, okay. If there's any challenges, just feel free to basically reach out or basically ask, okay. Right. So here's our task to do, or our assignment to do. Yeah, so it says state whether the following numbers are rational, irrational, or neither, okay, or neither. So maybe just before you start, I'd just like us to basically understand that again, what does neither imply? So neither implies that a number is not rational or irrational. So what number did we say is not rational or irrational? We said it's the number that is basically non-real. That is basically non-real. So in other words, find a number that state onto whether A belongs under rational, irrational, or neither. Explain whether B falls under rational, irrational, or neither, all the way through. Okay, so good luck, guys. Please attempt this exercise, okay, all the way up until you finish it, okay, and then we actually going to be running through the answers, okay, after this, all right, just to check how well you did, okay. But maybe just one clue, one tip: use the definitions that we basically studied in our class onto what rational numbers are, irrational numbers are, and what unreal numbers are, okay. So until we meet again in our until we meet again in our answer section. Okay, goodbye for now. Okay guys, so let us basically go through our answers. Okay, so A 0.25. all right, so 0.25 falls under rational numbers. Okay, so if you said rational numbers, you are correct. All right, reason for that is because 0.25 is a terminating decimal. Okay, and then B, negative 2 falls under rational numbers as well. Why? Because it is basically an integer, right? So therefore it falls under rational numbers. So we said our integers falls under our irrational numbers. And then what do you think C is? Okay, so C falls under irrational numbers. Why? Because we said pi falls under irrational numbers. Okay, and then if you add anything to an irrational number, your answer will always be irrational number. Okay, so therefore C falls under irrational number, and then the reason is because of that. Okay, right, so hence C becomes an basically a non-recurring basically decimal. Okay, then when it comes to D, okay, so what do you think D is? What do you think D is? All right, so D is irrational. Okay, why irrational? Because this is a square root, and then 10 is not a perfect square. So therefore D is irrational, because we said a square root of a number that is not a perfect square will always be an irrational number. How about E? E is neither. Correct. E is neither. It's not rational because there's a negative sign over there. And then we said unreal numbers are numbers whereby it's a square root of a negative number or any number divided by 0. Okay, and then how about F? Yes, so F is basically a rational number. Why? Because 6, this is a square root of a perfect square, and then square root of 16 is also equals to 4, and then this very same 4 is also a whole number, and then it's also an integer. Numbers and integers are basically rational numbers. Okay, and then G, what do you think G is? What do you think G is? Right, so G is a rational number. Why is G a rational number? Because 0 is actually a whole number. Okay, is basically a whole number. All right, and then H, so what do you think H is? Yes, that's true. H falls under neither. Okay, why? Because we said any number divided by 0 is actually unreal, as this is basically undefined. Okay, let us basically move to I. Okay, so what do you think I is? Okay, so let us quickly analyze I. So number one, I is a decimal. Okay, so if I is a decimal, we need to now see whether it's actually a recurring or a non-recurring decimal. So let us see. So we've got 0,54321, 54321, 54321. So this for me is actually recurring, as there is a pattern. So therefore this is a rational number. Okay, now let us look at J. Again, this is a decimal because there's a comma, and then there's dots there, which means it is actually non-terminating. It does not terminate. It basically continues forever. So let us look at the numbers to see whether or not there's a pattern. So 79311564805183446. There's no pattern at all. Okay, so it's non-recurring. So this will fall under your irrational numbers. Okay, let us look at K. Okay, so we've got a negative number there under a root sign. Okay, but is it unreal? Is it unreal? Okay, Then the answer is no. Okay, so why? Because this is basically a rational number. Okay, why? Because it's a cube root, not a square root. We said a cube root of a negative number does exist. So therefore, a cube root of negative 27 is basically negative 3, and then this negative 3 is an integer, and then we said integers fall under rational numbers. So a cube root of negative 27 is a rational number. Okay, and then let us basically move to L. Okay, right. So our L is basically, what is it? Yes, it is basically irrational. Why? Number one, we've got a cube root, not a square root, so it means this number here is real. It exists. So if it's real, is it rational or irrational? So as much as it's real, our 9 there is not a perfect cube. Okay, it's not a perfect cube. So therefore we said a cube root of any number that is not a perfect cube is always an irrational number. Let us look at M. Okay, so our M is basically pi over 3. Okay, pi over 3. And then again, this number here will fall under your irrational number. Okay, so why? Because if you take an irrational number, you can either add, divide, but then again, any fraction of an irrational number will always give you an irrational number. Okay, right. And then lastly, N. What do you think N is? Square root of 9 over 16. Okay, so square root of 9 over 16, this is basically a rational number. Okay, why is this a rational number? It's because, I hope you do recall, no, never mind guys. So square root of 9 over 16, okay, is basically the same as 3 over 4, okay, which is a fraction. Okay, you can see easy here that this is represented as a over b. Okay, so we've got a numerator and a denominator, and numerator and denominator are basically integers. Okay, or you can also call them whole numbers if you want to, because we've got our 3 over 4, and then this is basically a rational number. Okay, so I hope you enjoyed this exercise, and we are basically at the end of today's lesson. So tomorrow we are going to be looking at basically how to prove that a number is a rational number. Then we're also going to be looking at which basically rational number is found in between these two rational numbers and so forth. So we're going to be looking at and expanding on all those elements tomorrow. Okay, so until we meet again in our next lesson, goodbye for now.